In an ungrounded system without a neutral, it is indeed possible to establish an effective ground path. This relies on the equipment grounding conductor, often abbreviated as EGC. An equipment grounding conductor serves as a conductive pathway that connects the exposed metallic elements of electrical equipment to either the building's structural frame or a dedicated ground rod. Within ungrounded systems, the EGC is paramount. It acts as the primary route for fault currents and transient overvoltages to reach the ground, offering a low impedance path. The bonding of metal parts is crucial. In ungrounded systems, all exposed metallic components of both equipment and building structures must be interconnected using an equipment grounding conductor. This encompasses several items. Firstly, the metal enclosures that house electrical equipment. Secondly, conduit and raceways that provide pathways for electrical wiring. Thirdly, panels and boxes which serve as connection points and protective housings. Fourthly, building steel and piping which form part of the structural and utility infrastructure. And fifthly, heating, ventilation, and air conditioning, or HVAC, and plumbing systems which distribute essential services. The bonding of these metal parts, using an EGC, is what creates an effective ground path. When all metal parts are bonded together through the EGC, they establish a shared ground reference. During a fault, or when a surge occurs, electrical current can flow through these interconnected metal parts and then through the EGC, ultimately reaching the ground rod or the building's frame. This creates a safe and low impedance pathway that allows fault currents to flow and prevents the accumulation of dangerous voltages on electrical equipment. There are several advantages to maintaining an effective ground path in ungrounded systems. Firstly, it provides a means to safely dissipate fault currents, reducing the risk of electrical hazards. Secondly, it protects electrical equipment from potential damage caused by fault currents and overvoltages. Thirdly, it mitigates the risk of electrical shock hazards to personnel who may come into contact with electrical equipment. Fourthly, it enhances protection against transient overvoltages, which can damage sensitive electronic equipment. To ensure the creation of an effective ground path, it is important to consider several factors. The equipment grounding conductor, or EG, must be appropriately sized to handle the expected fault currents. All metal parts must be securely bonded to the EGC, ensuring a reliable connection. It is essential to consult and adhere to relevant electrical codes and standards to ensure that the grounding system complies with safety requirements. An ungrounded electrical system operates without a direct connection to ground, which differs from grounded systems that have a neutral conductor connected to ground at a service entrance. In an ungrounded system, the absence of a direct ground connection means that the system voltage is not intentionally referenced to ground. This design choice can offer benefits in certain applications, such as minimizing ground fault currents and enhancing system reliability in sensitive industrial processes. However, it also introduces unique considerations for ground fault detection and protection. Because there is no intentional ground reference, ground faults can be more difficult to detect. To address this, ungrounded systems typically employ ground fault detectors, which monitor the system for the presence of unintended ground paths. These detectors can trigger alarms or initiate system shutdowns when a ground fault is detected, preventing potential equipment damage and personnel hazard. Effective bonding practices are particularly crucial in ungrounded systems to provide a low impedance path for fault currents to return to the source. All metallic enclosures, raceways, and equipment frames must be properly bonded together and connected to a dedicated equipment grounding conductor, or EG. This ensures that fault currents can flow safely back to the power source, allowing overcurrent protection devices to operate and clear the fault. Regular inspection and testing of the grounding system are essential to verify its integrity and effectiveness. This includes visual inspections of bonding connections, as well as electrical tests to measure ground impedance and verify the continuity of grounding conductors. Any deficiencies identified during these inspections should be promptly addressed to maintain the safety and reliability of the electrical system. While ungrounded systems can offer advantages in specific applications, they require careful design, installation, and maintenance to ensure safe and reliable operation. It is important to consult with qualified electrical engineers and adhere to relevant codes and standards to implement appropriate grounding and ground fault protection measures. In electrical systems, impedance refers to the opposition to the flow of alternating current, analogous to resistance in direct current circuits, but also taking into account the effects of capacitance and inductance. A low impedance ground path is desirable because it allows fault currents to flow easily back to the source, enabling protective devices to quickly trip and clear the fault. High impedance ground paths, on the other hand, can impede the flow of fault current, potentially delaying the operation of protective devices and increasing the risk of equipment damage or electrical shock. The impedance of a grounding system is influenced by several factors, including the length and cross-sectional area of the grounding conductors, the quality of bonding connections, and the soil resistivity. Shorter and thicker grounding conductors generally offer lower impedance, as do secure and corrosion-free bonding connections. Soil resistivity varies depending on the composition and moisture content of the soil, with lower resistivity soils providing better grounding performance. The equipment grounding conductor, or EGC, plays a critical role in providing a low impedance ground path. The EGC is a dedicated conductor that runs alongside the circuit conductors and connects the metallic enclosures and frames of electrical equipment back to the grounding electrode system at the service entrance. The EGC provides a direct and intentional path for fault currents, minimizing impedance and ensuring that protective devices operate quickly and reliably. In addition to the EGC, bonding jumpers are used to connect metallic parts of equipment together, further reducing impedance and creating a more effective ground path. Bonding jumpers are typically short lengths of wire or metal straps that connect enclosures, raceways, and other metallic components. Proper bonding practices help to equalize the potential between different metal parts, preventing voltage differences that could create shock hazard. Regular testing of grounding impedance is an important part of maintaining a safe and effective electrical system. Ground impedance testers are used to measure the resistance of the ground path, ensuring that it meets the requirements of relevant electrical codes and standards. High ground impedance readings can indicate problems with grounding conductors, bonding connections, or soil conditions, which should be investigated and corrected promptly. A surge is a transient overvoltage event in an electrical system characterized by a sudden increase in voltage that can last for a very short duration, typically microseconds to milliseconds. Surges can be caused by a variety of factors, including lightning strikes, switching of electrical loads, and faults in the power system. These events can inject high-voltage transients into the electrical system, which can damage sensitive electronic equipment and pose a risk of electrical shock. Transient voltage surge suppressors, often abbreviated as TVSS, are devices designed to protect electrical equipment from the harmful effects of surges. These devices are installed in electrical panels or at the point of use, and they divert surge currents away from sensitive equipment, clamping the voltage to a safe level. TVSS devices typically use components such as metal oxide varistors, also known as MOV, and silicon avalanche diodes to provide surge protection. The effectiveness of a TVSS device depends on several factors, including its surge current capacity, voltage clamping level, and response time. Surge current capacity refers to the maximum amount of surge current that the device can safely handle without failing. Voltage clamping level is the maximum voltage that the device will allow to pass through to the protected equipment. Response time is the speed at which the device can react to a surge event. In addition to installing TVSS devices, proper grounding practices are essential for surge protection. A well-designed and maintained grounding system provides a low impedance path for surge currents to flow back to the source, reducing the voltage stress on protected equipment. The equipment grounding conductor, or EGC, plays a crucial role in surge protection by providing a direct path for surge currents to return to the power source. Bonding of metal parts is also important for surge protection. By bonding together all metallic enclosures, raceways, and equipment frames, a common ground reference is established, which helps to minimize voltage differences and prevent surge currents from flowing through unintended paths. Regular inspection and testing of surge protection devices are essential to ensure their continued effectiveness. TVSS devices can degrade over time due to repeated exposure to surge events, so it is important to periodically test their performance and replace them when necessary. Visual inspections should also be conducted to check for any signs of damage or deterioration. Ground fault circuit interrupters, often abbreviated as GFCIs, are safety devices designed to protect people from electrical shock hazards. GFCIs monitor the current flowing in the circuit conductors and quickly interrupt the power supply if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are designed to detect even small ground faults and trip within milliseconds, preventing serious injury or death. GFCIs work by comparing the current flowing in a hot conductor and the neutral conductor. Under normal conditions, these currents should be equal. However, if a ground fault occurs, some of the current will flow through an unintended path to ground, creating an imbalance between the hot and neutral currents. The GFCI detects this imbalance and quickly trips the circuit, interrupting the power supply. GFCIs are commonly installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. They are typically installed in receptacles or circuit breakers. Regular testing of GFCIs is essential to ensure their continued effectiveness. GFCIs should be tested monthly by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Electrical codes and standards provide detailed requirements for grounding and bonding in electrical systems. These codes are developed by organizations such as the National Fire Protection Association, often abbreviated as NFPA, and the Institute of Electrical and Electronics Engineers, often abbreviated as IEE. They are updated regularly to reflect the latest safety practices and technological advancements. The National Electrical Code, often abbreviated as NEC, is the most widely adopted electrical code in the United States. The NEC provides comprehensive requirements for the safe installation of electrical wiring and equipment. Chapter 2.5 of the NEC covers grounding and bonding. Article 250.4 provides general requirements for grounding and bonding, including the requirement for an effective ground fault current path. Article 250.24 covers grounding of service equipment, including the requirements for grounding electrodes and grounding electrode conductors. Article 250.92 covers bonding of metal enclosures and raceways. Article 250.118 lists acceptable types of equipment grounding conductors. IEE Standard 142, also known as the Green Book, provides recommended practices for grounding and bonding of industrial and commercial power systems. The Green Book provides detailed guidance on the design, installation, and testing of grounding systems. It covers topics such as grounding electrodes, grounding conductors, bonding techniques, and surge protection. Electrical codes and standards are essential for ensuring the safety and reliability of electrical systems. They provide a framework for the design, installation, and maintenance of electrical systems, helping to prevent electrical hazards and protect people and property. Compliance with electrical codes and standards is typically required by law, and it is the responsibility of electrical contractors, engineers, and inspectors to ensure that electrical systems are installed and maintained in accordance with these requirements. A qualified electrical engineer is a professional who has the education, training, and experience to design, install, and maintain electrical systems safely and effectively. The electrical engineers typically hold a bachelor's degree in electrical engineering, and they may also have advanced degrees or professional certifications. Qualified electrical engineers have a thorough understanding of electrical codes and standards, and they are able to apply this knowledge to the design and installation of electrical systems. They are also able to perform calculations to determine the appropriate size and type of electrical equipment, and they are able to troubleshoot and repair electrical problems. Hiring a qualified electrical engineer is essential for ensuring the safety and reliability of electrical systems. Electrical engineers can help to design electrical systems that meet the specific needs of a building or facility, and they can ensure that the electrical system is installed in accordance with all applicable codes and standards. They can also provide ongoing maintenance and support to ensure that the electrical system continues to operate safely and effectively. Continuing education is essential for electrical engineers to stay up to date with the latest technological advancements and safety practices. Electrical engineering is a rapidly evolving field, and new technologies and techniques are constantly being developed. Continuing education courses and seminars can help electrical engineers to stay abreast of these changes and to improve their skills and knowledge. Many professional organizations offer continuing education opportunities for electrical engineers. These organizations include the Institute of Electrical and Electronics Engineers, often abbreviated as IEE, the National Society of Professional Engineers, often abbreviated as NSP, and the International Association of Electrical Inspectors, often abbreviated as IE. Completing continuing education courses can help electrical engineers to maintain their professional certifications and to meet the continuing education requirements of the state or local licensing board.